Welcome to the Designing, Implementing, and Using Reactive APIs talk. Please forgive us. We are basically like walking wounded up here. I've got some busted up ribs and a bad head cold, and he ate something a bit dodgy last night. So we'll try and keep it together and make sure you guys get some good content out of this. So my name is Ben Hale. I am the lead of the Cloud Foundry Java experience, which is a title that means basically nothing. What it really means is if you are Cloud Foundry developers, I basically sit at the nexus of Java development on Cloud Foundry. All the things that we try and do when we talk about running Java applications on top of Cloud Foundry runs through teams that I am a member of. We're here today to talk about reactive APIs, and we're going to do that a little bit in the context of Cloud Foundry, so it's great if you sort of have some idea, but don't worry. If you're not Cloud Foundry users, you're still going to get a whole lot out of this because we just use it as an example, but all of it is sort of Spring and Java specific. My co-host here today is Paul Harris. Paul.
Hi, everyone. My name is Paul Harris, as Ben said. I suppose I'm the lead developer, as well as almost 100% of the developers on the Cloud Foundry client. Before that, I was doing stuff on TC Server and something called DM Server. I don't know if anybody here's got any memory of that. A long time ago now.
Yeah. Great. So before we get started in the talk today, how many of you today are already using Project Reactor or RxJava or doing some sort of reactive programming? Good. So there's some, call it like 10% of you. How many of you are here today because after 2 years of keynotes saying reactive is the future, you are terrified that you are about to miss something, right? Yeah. The good news is we're still right on the early bits of reactive programming, and so we're going to talk a little bit about what you might want to do with it. So this is the most hilarious slide I've ever written, absolutely. Introduction to reactive programming, you're going to get 5 bullet points. Obviously, reactive programming is way, way, way more complex than this. But it does sort of give you an idea of what we're looking at when it comes time to do reactive programming. So when we talk about reactive, broadly what we're describing is we want a way to define event-driven systems in a better way than we have to date with imperative-style programming. We want to take imperative, which is sort of what we all know as Java developers, and we want to move that imperative logic in such a way that it becomes asynchronous and non-blocking and using a functional style. So effectively what we want to say is all the code that we've written today, if we need it to be asynchronous, we'd have to use Java threads or something that builds on top of Java threads. That's not awesome. If we want to use the non-blocking I/O APIs inside of Java, it's not awesome from the imperative side. If we want to do things like functional style code, a lot of reuse of very simple methods, using lambdas a lot in line, it's not really awesome. So what reactive programming aims to do is to take all of that logic that we've already written today, but put it into a framework that's a lot easier to understand, a lot easier to reason about, and most importantly, that takes care of a lot of this stuff behind the scenes so that we don't have to. One of the final points, though, when we talk about reactive programming is something that most people don't really think of as sort of a first-class citizen when it comes to programming, and that's that we want to make sure that our application is stable and scalable when it accesses external systems. We'll talk about this a lot sort of as we go along, but one of the key problems that reactive programming, and specifically this sort of back pressure style reactive programming that the Spring team is endorsing, is that what happens when you have a whole lot of connections all hitting your application simultaneously, and they're all going back to the database, and they're all grabbing a ton of data, right? Under high load, it's very, very hard to reason about how an imperative program is going to work. Is it about to go accidentally pull 10 million rows of data into your VM, blow up the heap, and the whole thing falls over under the highest possible load? Well, one of the things that we're aiming for with reactive programming is to say that's not going to happen. We want to get to a point where we can predict what the behavior will be under the peak load of a particular system. We want to know that if we have tens of thousands of connections all coming in simultaneously, if they're all pulling data out of the database, there is a maximum limit that we can reason about when it comes to memory and CPU usage so that we can plan for that ahead of time and guarantee that we don't have unexpected behaviors. So we're going to talk about reactive programming today in the context of this project called the Cloud Foundry Java Client. And as I said before, it's not critical that you know what Cloud Foundry is, but it is actually the first project that we built on top of Project Reactor, and really the first major API that was delivered by Pivotal. But sort of I come from the Spring world, from 2005 kind of thing. Making sure that we are able to, sort of prove out what we believed with the reactive APIs before Spring came along with them, and that's what this client did. It's a language binding that sits on top of Cloud Foundry's RESTful APIs. It's got security with OAuth, transmits large JSON payloads back and forth, has to do tons of serialization and deserialization, and we find out that the API is very, very low level. There's about 550, 600 maybe APIs in Cloud Foundry itself. So we're looking for the ability to write a library that not only can access every single one of those low-level APIs, but when we start talking about concepts that sort of users deal with Cloud Foundry, and so any of you who've either done or have seen a demo of someone saying CF push an application, right? That's not a single API call. In fact, it's an orchestration. I'm sure Paul can tell you with furrowed brow that what that actually is an orchestration of like a dozen different network calls, a bunch of waiting around and polling and things like that. It's really, really complex stuff that encapsulates all that stuff that we described on the slide before. It's asynchronous. It's non-blocking. We have to deal with error cases that potentially fall back to something. We have to do periodic polling to go back to those APIs and find out when server-side behaviors have completed. So this was a really, really good proving ground for the reactive APIs and for the Reactor project, because this is exactly the kind of system that we would expect your average reactive programmer to be trying to do. The same kinds of large numbers of network calls that are all orchestrated back together. And so the Cloud Foundry Java Client is that. And we're going to use that today as a lens to sort of describe some of the things that we actually learned about. So one of the reasons that we wanted the Java client to exist in its current form was because Java had actually become the most important way to orchestrate Cloud Foundry. And there are various reasons for this. The existence of a Java client in the first place is a good reason. A lot of the application developers that were pushing to Cloud Foundry were Java developers, so they already had the skill and they wanted to do some sort of orchestration. But we wanted to make sure that the API that those users were dealing with was strongly typed. Because you could imagine a scenario like this, trying to access an API where we say, okay, here's a map. It's name, it's application, it's build pack, and there are some values in there. But you can imagine as APIs evolve, or you are just typing in here saying, name, did I get the capitalization right? Is build pack spelled correctly? Do I need hyphens? Do I need camel case? What exactly is going on? And when I go back and say response.getID at the other end, what exactly am I getting back? Is that a string? Is it is it a number and stuff like that? So we wanted to make sure that we could do something that was much more strongly typed. And so we wanted to see an API that looked a lot like this. We take our applications, we want to push an application. We say it's got a name. Here's where you go get the jar that you're trying to push. I want you to use the Java build pack. And when it comes back, I have a strongly typed ID. In this particular case, it's a string is what comes back. And so this is sort of what reactive programming looks like to us, right? Like, there's a lot of sort of builder-style APIs. There's a lot of strong typing and sort of inline kind of programming to handle these kinds of Cloud Foundry interactions. And so, as I said, this sort of high latency model, not only is there latency because you are making a lot of calls over to the network, but the Cloud Foundry API, the cloud controller, is not the most highly performant server you might ever connect to. And so we want to make sure that this sort of asynchronous and highly concurrent user, because it's really, really common that we need to make 3 different network calls, get the payloads back, transform them in some way before we pass them on, is really, really a good fit for us here. And it also helped that at the time, sort of Project Reactor's 3.0 effort was starting to spin up. And I spent a remarkable number of hours with Stefan, the lead of Reactor, on Screen Hero. He was in London and I was here in San Francisco. So he was having some late nights and I was having some very early mornings. In the end, we decided to solve this problem. He moved here to San Francisco, and now he sits right next to me, so it makes parenting quite a lot easier to do. But that level of integration, as he sort of started working on what should this API be, how should this thing operate, what kind of things do you think your average reactive developer is trying to do, what operations should we add? I was able to, sort of influence that, and vice versa. He would come to me and say, okay, the thing you've done here isn't particularly reactive. Here's, what we would sort of expect out of it. And there's this sort of back and forth that really strengthened both projects to the point now that Reactor 3.0 and even 3.1 has been released now as GA. The Spring team is building on top of these things. We have a really, really good foundation. We have lots of users using the Java client, getting their first exposure to this as well, and coming back to us. And all of this is just a great feedback loop, great feedback cycles here as we improve both of these different projects. So one of the key differences, I think, about this talk from almost every other talk you're going to see about reactive programming at this particular conference is all of those other talks are the developers of those particular frameworks, the developers of Reactor, the developers of Flux or something like that have built these amazing, flexible frameworks that allow you to program any way you want. There's, in the true Spring tradition, there's, 40 different return types you might have, and your programming style could be this or it could be that, because that's what those frameworks are there for. Reactor has, a ton of different operators for you to choose what you think the best way to do things are. But this talk is different, because this talk is absolutely born of us implementing something on top of Reactor, and that means we have opinions. And not just minor opinions. We have very, very strong opinions. As I said, we're looking at 550, 600 different APIs that we designed on top of this thing. We have a couple of things that we've seen. So when it comes to designing an API with Reactor and our opinions on it, we need to sort of take a step back all the way to the very, very beginning. When should I use it? Because reactive programming is not perfect for everything. There are, I don't want to say a ton of downsides, but there are very significant downsides to using reactive programming. I'd say today probably the biggest one is it's much harder to debug problems when they're happening in reactive programming. However, the Reactor team is working on it. They're working with IDEs to make it better, so don't let that scare you away. But there are certain places where when you look at them, you say, this is obviously a very big win to use reactive programming, to use Reactor here, because the value that we will gain significantly outweighs the downside of us trying to use it in the first place. And so the easiest one is anytime you are going off to do some kind of networking, because there's all sorts of latencies involved. You need to make sure that you aren't blocking threads when you're waiting on systems to respond. What happens when there's a failure over on the other end? Should I be having a bunch of timeouts everywhere? Should I have one global timeout for the entire orchestration? If it fails, should I retry this one little bit, or should I go all the way back out and try, the entire sort of behavior again? These things are all really, really good places for using reactive, because the programming style that we're going to see makes it very easy to describe those things. You can say, in the middle of any bit of a flow, you can say .timeout and put a duration in there. And so you can have these very fine-grained timeouts all over the case, all over your code. Or you can have a .retry so that this one particular thing, you might want to retry it when it fails, but this one other request over here, if it fails, it means it's never going to work, and so you don't retry that one. So networking basically is a really, really good idea. Highly concurrent operations as well, so things where you need to go and make 10 network requests simultaneously, or you need to go make a bunch of CPU-intensive calculations on different threads on the same system. Another great place for reactive programming, because one of the sort of standard features of a reactive framework is this idea that you don't have to manage threading very much, right? You can obviously, if we take a look at Reactor, there are ways that you can force it onto different thread pools, the execution onto different thread pools. But in general, you can say, okay, flat map this out, and it will just go off in parallel and put things on different threads and utilize the resources that your system has to the best that it possibly can to make sure you're utilizing all of the power that's available to you. And then finally, scalability. When we say scalability here, really what we're talking about is efficiency. We've long sort of put off the fact that at the moment, sort of the standard servlet model of one connection per one thread blocking APIs all over the place means that under very high connection loads, especially in the microservice world where you're making calls back out to the other systems across the network with latency and things like that, we're seeing huge horizontal scalability, right? People are running 5, 10, 20, 50 instances of the same stateless application just so they can handle the loads that need to come in. And one of the promises of using reactive and specifically non-blocking style I/O is you break that linkage between an incoming connection and a thread and allows you to reutilize those threads. And like, it's not even close. Tomcat sort of starts with 200 threads, and I can't tell you the number of times I've seen customers doing 1,000 threads inside of Tomcat because they need to handle all these connections. Netty has the same number as your processor. So like Netty can handle higher loads for non-blocking I/O with 4 threads than Tomcat can with 200 or 300. But only for use cases where you have a problem in this case, right? So all of these things are really, really obvious, but you should also take a step back and say, am I actually seeing problems with these particular things? So if you're on a system where you find out that you're running out of connections are being refused without having to stall and creating a ton of latency, and so you're doing horizontal scalability, but your CPU usage isn't that high, sort of 10, 15%, it's basically sitting around idle, that's a really, really good idea. But if you're on smaller systems that aren't running out of connections, or you're on systems where, yeah, you're running out of connections, but the CPUs are pegged at the same time, there's no real need to introduce the complexity of reactive programming. It's definitely a trade-off between those two that you're trying to take a look at. So if we take a step back and we say, okay, I've decided that I want to do a reactive API, what kind of things am I dealing with, right? So in Reactor, and we're going to talk about Reactor specifically here since obviously it's near and dear to our heart, we built on top of it, but there are other reactive APIs in the world, so like RxJava and things like that. All of them are sort of converging on this thing called the reactive streams specification, which defines a very low-level interop set of interfaces and this concept of back pressure. But in Reactor, there are 2 main types. And they are conceptually the Flux type that returns 0 to n values, basically a stream of values flowing through the system, and a mono, 0 or 1 values, right? And it turns out that inside the Java client, we are almost exclusively on the mono side, right? You are asking for a payload. Give me some metadata about this particular application. But we also end up, and this is sort of possibly counterintuitive to a lot of people, we also end up returning monos of collections. Tell me about the metadata for each instance, for all of the instances of a particular application. In that case, we still return a mono. We don't return a Flux because it's just a collection of all of that metadata. And there are lots of operators that you can split a collection back down into a Flux if that's the way you want to handle it. But we find that in most cases, we want to maintain that one request, one response kind of mapping. And then even the collections that came back from that particular response, we hand back as a mono of that particular collection. So what does it mean to use a Flux response? And so that's what we see right here, right? We've got this idea of listing a set of applications. And so we're going to go off and do something. In this particular case, we are going to make a network call. It's going to return something, some application kind of thing. And that means that when that comes back, I get a Flux, and that Flux is guaranteeing to return me 0 or n of these application things. And we have some operators that go on the end of that. And so what we're actually going to do, we use a method reference here if you're not familiar with it from Java 8, and we say, given an application object coming through here, I want you to get the name of that particular thing. So if we take a look at that final one, effectively what happens is there's a chain back to list applications. Each application that flows through has its name returned. When we subscribe to it, we're going to print out the name of each one of these things. On the mono side, we don't have a flow. We still use the same kind of operators to do that work. One of the key things that Reactor has really, really focused on is having, since we have sort of these 2 worlds, this Flux that has 0 to n responses and a mono that has 0 or 1 responses, making sure that where things are the same, things like mapping a name from an object, whether there's 0, n, 1, or 0, all have the same kind of operators attached to them. So in this particular case, we go off and list those applications. We get the names from them. But in this case, we return it as a list, right? We want to return that collection of things, not a flux full of them, but just put them in a list for me. Because when I use it at the other end, I don't need to iterate over it as part of this thing I'm doing. Really, what I want to do is take a look at the entire collection and find out some answer from it. So we collect it as a list. Again, it stays as one of these monotypes. Here, I'm either going to have, excuse me, 0 lists, or I will have 1 list, and then I can find out some answer from it. You can see in this case, we map it to whether or not this particular collection contained a thing. So those are sort of the 2 building block types for designing these APIs. You're almost always returning a mono or a flux of something. And those can be anything, any object in Java. They could be just an application, or they could be a collection of strings. Anything is possible there. So unlike sort of standard imperative APIs, void isn't a return type. Null isn't even a sort of a valid thing to flow through one of these. Everything returns something in the reactive world. And the reason for this is because, and this is, when I first started doing reactive programming, I cannot tell you how long it took me to get my head around this. A reactive flow, like all the code that you've seen so far, defines sort of a framework, an infrastructure, if you will, of when data comes, this is what I want to do. So the execution of one of those methods builds this framework, but nothing actually happens until someone subscribes to that flux or that mono and basically starts requesting data from wherever the far end of that flow started. Nothing happens. And that's why you actually have to return something, because you have to have something for the caller to actually subscribe to. If you just sort of said, okay, I want to create this flow and I want to subscribe to it sort of in here and I return void, then nothing is effectively happening there. It's building this whole data structure in memory, allocating a bunch of instances and things like that, and then they're all garbage collected and nothing has really happened. So you might see something like, oh, I want you to go call the REST template, call delete. That is a blocking operation. That means that this method starts, and it goes off, and it makes a network request, and it holds it open, holds it open, holds it open. The server responds, yep, I was able to delete successfully, and the method returns, and the main method returns out at the end. But the reactive style is something like this, where we go off and call a delete, right? So we're returning immediately. This method executes completely. So by the time it gets back to main, sort of the line that says delete test ID, nothing has happened. No network request has happened at that point. It's only at the point that we subscribe to that this entire framework that we built then is executed. Then the networking happens. And there's sort of this whole CountDownLatch thing around it. Ignore that for the moment. We're going to come back to exactly why this is a really useful construct to do something like this. But suffice to say that until that subscribe happens, no network request has been made, which is obviously very, very different from this kind of programming model here where void was okay. And again, we had to return a mono of some kind. In this particular case, it's something called a mono void, which basically says that I'm not going to send any data. I'm not going to send a string that says OK or an integer that says 200 or something like that. All I want you to know is when this thing completes. Because it turns out if you look at sort of the subscribe method signature, there are 3 components to it. And the first one is, what should I do when the data comes? And in this case, it's just a throwaway, right? And does nothing, because nothing will ever come. It's a void. What happens if there's an error? Well, I just want to print the stack trace. There's nothing I can really do if delete fails. Or maybe there is. Maybe we go and do something else. And then finally, what do I do when this whole thing completes? It goes to the CountDownLatch and sort of releases the await that's happening. And so the key thing to take away from this is a mono is useful even in the case where it returns 0, because it will always complete. There's a marker effectively saying that asynchronous non-blocking execution that you had asked for when you did subscribe, it's not going to return any data to you, but it will let you know when that thing is complete instead. Big difference from our imperative API with a void. So now we start talking a little bit about what does it mean now when I start writing code that uses these APIs. We know that they're going to need to return a Flux and a mono, but we need to do other stuff. It's not enough to just simply say delete. And so we have found that you want to define methods to be small and reusable. There's a couple reasons. The big one, reusable methods are easily composable into larger operations, and they're very, very useful to, you end up writing very small functions that are useful not only in the class that you're in, but in other classes very, very often. One of the really nice things about writing methods that are really, really small as well is that it puts you in a position where you don't actually care if the method is being executed sort of sequentially along with a bunch of other things in a chain, or whether it's been splayed out and it's running in parallel with a bunch of other things. Because as we take a look at all of that code, it's important to remember that we've not stated anything about what thread any of that execution happens on. And you'll find out, especially when you start doing networking, that the request goes out on one thread and the response comes back in on another thread. And that's really, really key, because that means that you don't really know what the context is that any one of these methods is going to be executing. So keeping them very, very small makes it so it doesn't really matter. You're doing something very, very componentized. There's this thing called fusion inside of Reactor where if it turns out everything's going to execute on the same thread, it sort of removes all of the overhead of getting between these little lambdas and executes those lambdas just straight next to one another, bang, 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 and sort of compresses them for the efficiency you might be looking for in the first place. So we take a look at reusable methods. We have this reusable method that goes off and gets a page. So this is listing applications is a paginated response because you can have hundreds of thousands of applications inside of a Cloud Foundry instance. So in this particular case, we know that we need page 1, page 2, page 3. And I don't have to re-implement that network call, that go get me list applications request, because I can just say, get me a page. And once that page comes back, I can say, OK, I've gotten the first page. Now you tell me how many more pages are left. Is there a second page? Is there a 100th page? And now I can just sort of iterate over this and say, OK, get me to page 2, page 3, page 4, page 5. If it comes back and tells me there was only one page in the first place, I effectively have a range from 2 to 1, which is nothing. And so no new executions happen at that particular point. But we've reused this sort of get page thing without having to re-implement the same code. And when I sort of started working on Cloud Foundry, 3 or 4 years ago now, I took this step from being an exclusive Java developer. I actually became a Ruby developer, basically, in my day-to-day. And one of the things that I really took away from the Ruby community that they're more committed to than the Java community generally is this idea of very, very compact methods. Like, it's totally reasonable in Ruby for you to write a one-liner method simply to change the name of another existing method, right, that's going to delegate out to something else, purely for readability. And Java developers don't generally do that. But it is something that if you can internalize it, if you can say that basically every sort of single atomic thing that I want to do, I want to go get a page of things, right? If you can internalize that you can put that into a method, it puts you in a position where your code looks a lot different and it's a lot more concise and it ends up being a lot more readable in the long run. And so now I'm going to hand it over to Paul to talk a little bit about implementing those kinds of designs.
OK, thanks, Ben. So we're going to start off with a nice bold statement that all significant performance improvements come from concurrency. I don't think actually that's all that controversial, that processors get faster, disks get faster, and so on. But if you can do 10 calls at the same time rather than stacking them up sequentially, then the likelihood is you're going to get better performance. So no matter how many cores, the more cores you can throw at it, the better potential performance you have. The problem with that is that concurrency is hard to do properly. It is something that you can do, and you can sweat all the details, but quite tricky. So one of the benefits of reactive frameworks, and particularly Project Reactor that we've been using, is that they allow you to define sequential and parallel relationships between operations. So you don't have to worry about it. You set up the basic idea, here's what I want, and then let Reactor deal with it. So if we go back to the code that we were looking at before, where we've got our page, and then we're going to potentially look up a number of other pages, what we're saying is, I want to do this first call. I want to get my first page, and then I want to get an unknown number of other pages from 0 to however many. So I'm just defining that as a simple flow. I've got a single thing that happens, and then depending on what comes out of that, I want some other things to happen, and I don't really want to worry about anything else. So by defining that, we're saying to Project Reactor, you deal with the coordination, you figure out how many calls there need to be made, you sort out the threads, do everything for me, and just at the end of it, I'll get my data that I can then sys out. So naturally, we want to do all the sorts of things that we do in imperative programming when we're doing our reactive programming. An obvious one there is conditional logic. One of the slight oddities or the new things for Reactor coming from the imperative world is that errors pass through. Errors are essentially a value the same as a 0 or a string or whatever it might be. They are just things that get passed down the flow. As they're being passed down, we can just continue to pass them on and say, look, something went wrong, here you go. Or we can take actions based on them. Perhaps it's an error that we're actually expecting and we want to be able to handle something. So if we look at this call here, we're doing an application request. So we're retrieving some information about an application on Cloud Foundry. Specifically, we're looking at the statistics. So it's things like uptime and CPU usage, that kind of thing. We make that request, and hopefully we'll get back some information and we can pass that back. And you can see at the top line there, we pass back a mono of an app stats response. But it's potentially, the application may not be running. So Cloud Foundry will return an error to us saying, I can't tell you about uptime because it's not up. That's a normal error. Nothing has gone wrong. The application just isn't running. So we want to be able to handle that. We know that's a likely outcome, so we want to be able to handle it. The way we do that is we observe that there has been an error. We consume that error. We don't actually use the error to do anything. We just say, I will return an empty app stats response. So at the end of the day, whoever's called us will get back an app stats response, and it will either be populated with a bunch of useful stuff, or it will just say, yeah, there's nothing to know here. So that's conditional logic based on errors. We can also do conditional logic based on nothing, in a way. So as Ben was saying, we get back complete messages saying, I have done the thing that you asked me to do. I don't have anything to tell you. I just want you to know I'm done. So it's kind of like returning a null when we're doing imperative logic. Again, we can pass that information down through the flow to whoever's ultimately subscribed to us. Or we can, again, start to switch behavior, do new things with that, generate new outcomes based on that result. So here's an example again from Cloud Foundry. We're going to get a domain based on an ID that you've given me. Because you've given me the ID, I know that that domain must exist somewhere in Cloud Foundry. You didn't just make it up. So I'm going to start off by looking at all the private domains on Cloud Foundry. And hopefully that will find the ID that matches, and I can return that back to you. But potentially, it's not a private domain, it's a shared domain. And I can't tell that from the ID that you've given me, so I have to try both. So if request private domains returns nothing to me, it says, no, I checked, there was nothing there, I'm complete. I can do a switch if empty. I can say, oh, the previous request was empty, so I'm now going to go and check request shared domains, and hopefully it will come back with a response, and I can then pass that back to whoever called me. We can start to get more complicated than that. So in this case, I want to retrieve a domain ID. It's going to be a mono with a string. It's just an ID. And in this case, I'm doing the request based on a name. So it's a string that the user has provided to me. And because it's a string of a name, I don't know that this thing actually exists in there. It's not some unique ID. So I have to be a bit more careful about the search that I do and the results that I'll ultimately give back. So I start the same way, basically. I say, give me a private domain ID. It will go and look at all the private domains, see if it can find a match for the name. If it can, it returns, I've got my ID back, this will give back the ID as a monostring. If it doesn't find one, then it's switch if empty, so it got an empty signal back from the get private domain ID, and I will call the get shared domain ID, again with the name, and say, have you got one of these? And if it finds it, it returns the ID, and I get a monostring returned. If that doesn't work, then I do a second switch if empty. And I say, I couldn't find it as a private domain, I couldn't find it as a shared domain, so as far as I can tell, this domain doesn't exist. So I'm returning an error, an illegal state exception, and a useful message. And again, that's an error that goes on to the next person who's called me. Maybe they'll do something useful with it, maybe they'll just kick up an error for the user. The most obvious, perhaps, use of conditional logic is to take values that we produce from one step and make decisions based on that value to do something else. The trick here is that it can start to get rather complicated. We've already seen a couple of switch if empties stacked up. That's fine, but as you'll see in a moment, it can get rather more complicated than that. So we know that we can use imperative logic if we want to. So here's a conditional logic avoiding imperative. I'm kind of hoping that this text will look a bit intimidating to you. That's part of the point of it. And I'm hoping it will be so intimidating you won't actually try to run it, because I'm not entirely sure it would run. The basic idea is we start off with a mono. We need to get into reactive mode, as it were. So we have a mono of a domain. And I will then filter on it and say, if they didn't actually give me something, if the value I was given was null, then I want to get shared domain IDs, do my switch if empty that we saw before, take a value from it, and if I don't get anything back, I'll return domain not found. There's a question, sorry?
Yeah. Why does this method doesn't have throws illegal state exception? The question is, why doesn't this method have a throws illegal state exception? Because at no point does it actually throw an illegal state exception, right? What it actually does is it generates a mono containing an illegal state exception error. But what's returned from this, remember, no execution has happened during any of this time. What's actually happening is that it's returning this flow, this framework, ready to execute, right? And so what you end up finding is that methods that return flows like this, return monos and return fluxes, never, ever, ever return exceptions, right? Their exceptions become an integral part of the execution of these flows, not of the creation of the flows themselves. And you're forced to handle those exceptions directly as if they were a value being passed through. That's one of the key differences, is this requirement, like, eventually you're seeing exceptions flowing through and you can intercept them or do something, or you can let them flow through for someone else to do it. But it is a first-class citizen, a thing that when you subscribe, you should be dealing with.
Okay. So that was option one. But option two is we were given a domain that we should be searching on. So I go to my third switch if empty. I do a get private domain. If that comes back empty, I do a switch if empty. I get shared domain if that's empty. Switch if empty, domain with a particular name is not found. As I say, probably that would work, but having 4 switch if empties in a row, I can't follow the logic. I don't understand what's going on there, really. So when you've got something like that, you can actually switch to a partially imperative way of doing things, and hopefully that will look very familiar to you. If domain's null, do something else, do something else. The key of that, around that is that each of those 2 things that you do is a reactive flow. So we're not changing the imperative nature or the reactive nature of it. We're just saying, choose between these 2 reactive flows, return back that bundle of reactiveness, if you like. There's a technical expression for you. And from the application's point of view, it's just some reactive flow that I will continue with, and everything will work out fine. So don't be afraid to use imperative logic, because it just solves a whole lot of headaches. Just be careful that at the heart of it, you still keep that reactive nature. Testing. So as it says there, most useful flows will be asynchronous. That's the reason that you're using reactive. But because of the nature of the way they operate, testing frameworks tend to be aggressively synchronous. They want to get the results as soon as they can so they can report success or failure. So to compensate for this, if you're rolling your own testing for reactive, you need to block the main thread and make test assertions in the asynchronous thread. So here's a naive way of doing things. We're going to start with a single string that we've got mono just alpha. We subscribe to it, and we're doing something with schedulers there to be correct that makes sure that we will get the poor behavior that we want. We subscribe to it, and we say, I'm expecting Bravo. And when I run it, it passes, which is great, except it's not supposed to pass because we should have been getting alpha, and we've said we wanted Bravo. The reason that's happened is because we did the subscribe, JUnit, which is what we're using here, said, did I get a failure? No, I didn't get a failure, and report success. And in the meantime, the actual test that we're trying to do has happened, reports, no, it didn't work properly, and there's nobody listening to say, all right, I see that you failed. So we need to handle the fact that we've got threading issues there, that things are happening on different threads, and we need to keep things synchronized. And the way we do that, as Ben mentioned before, is to use a CountDownLatch. We're going to do a little bit more about CountDownLatches later on because they are useful in other contexts. But basically what we say is, on that subscribe line, here's the thing that I actually want you to do. Here is when, on next, when I get a value in, here's what I want to do with it. If there is an exception, a failure, then I want to count down my latch. And when everything is complete, I also want to count down my latch. One of the things to be aware of is that if you have an exception, that is not the same as an on-complete. They are mutually exclusive. So if you're doing something on complete that you want to happen, if there's an error, you need to manually do it yourself. So what happens in this scenario, if we run it, the latch makes sure that we wait until we've got a result from our subscriber before it does the test. And when it does the test, it fails. So you've just seen some complications of doing testing yourself with having to do blocking. And that's just one consideration that you've got when you're doing testing. You also need to be able to cope with things like multiple value assertions, expected errors, unexpected errors. It starts to stack up the amount of work that you're going to have to do if you're going to test with it. Fortunately, Reactor took care of that for us, and we can use something called StepVerifier to take care of the blocking for us and to do all these other useful testing things. So, starting off with a pretty simple example, we have a Flux, so it's going to emit two values, alpha and Bravo. We're going to use create a StepVerifier that will sit in the way of that flux, consume that flux, and then lets us access the information that the flux is creating, and we can start doing tests against it. So you can see here we do an expect next alpha, and then Bravo. At the end, we do expect complete, and then the final thing, the thing you mustn't forget, is to do a verify to say, I actually want this to happen. It's effectively a subscribe. I want this thing to occur. We give it a timeout because otherwise we could wait forever, which is not good for testing. And I think, yeah, you're going to have to take my word for it. That worked. I've used expect next there, but you have a range of other tools available to you. You could, for example, do expect next count and just say, I'm expecting two things to come out of this. Perhaps that's sufficient for what you're doing. You can start to consume the flow that's coming back to you and do all sorts of tests and use all the asserts that you know about to get much more sophisticated testing. Kind of an example of that is if you have an expected error. So this particular test, going back to our domain stuff again, I'm going to try and share a domain, except this is a domain that can't be shared, and I know that in advance because it's my test. So I do my little piece of setup. I create a StepVerifier, and I know that I'm going to get an error, so I've said consume the error that I expect, and then I can start making assertions on it. I can say it has, it's an illegal argument exception, and I've got the message that I know I'm going to be expecting. And again, I do the verify to say, let's do this test. And again, you'll have to take my word for it, that works. Okay, so that's some of the implementation details that we've been using. Let's take a look at actually using it. Now, this is where we get to the countdown latches. If you're running in something like a servlet container, so maybe Tomcat, we know that Reactive plays well there because it has Tomcat or whatever will have processes that are long-lived, because Reactor can only control the threads that it's particularly concerned with. If it's the underpinnings of it get taken away before it's finished, it doesn't have anything it can control that with. So if you're playing in Tomcat, you're fine, probably. But if you're working on testing, as we've just seen, or if you are using main methods, for example, they will aggressively try to terminate, and that can cause the problems that we were seeing in the test. So if I'm using, in this example, I've got a mono of alpha, again, very simple. I'm going to delay my subscription by a second. So I'm not actually going to act on the subscription that I'm doing for 1 second. I subscribe, and then I want to print out the value that I get through. And when I run this in my main method, it completes successfully because nothing went wrong, but I don't actually get the sys out that I was expecting. I don't have alpha printed. And that's because, again, similar to the testing, I was waiting a second before I actually produced the output, and in the meantime, my main method has said, we're done. I've completed everything you wanted me to complete. So what we want to do instead is use CountDownLatch to make sure that we're waiting for the subscriber. So again, I have a single mono just alpha, so single string coming out. I'm going to wait again for a second. But this time, I'm subscribing. I've got an onNext condition. I'm saying I want to sys out whatever I get. I have an error condition on error, so I will count down my latch. So I don't want to do anything with this error. I just want to say whatever it does means I have now finished, so I need to complete. And the final on complete is, again, count down the latch. So whichever of these two options I get, if I get an exception or I get a complete, I know that the latch will count down, and then I know that my process will actually complete. And if I do that, I get the same result, except this time I have the printout that I was expecting. I should actually point out that that's quite a lot of boilerplate that you would include. In practice, what we tend to do is that gets buried in a method that you call somewhere else. So you can do that to make life a lot easier for yourself, and you just call your own subscriber. I don't think we've got an example of that now. OK, so we've talked a lot about reactive. Most of you, I imagine, are still in the imperative world. And even if you switch over to the reactive world, you're still going to be interacting with imperative systems for potentially a long time to come. So you need to be able to interface between reactive and imperative. You can, I'm going to be really careful here, you can use blocking. You can convert your system from being reactive to blocking. And it's fairly straightforward. We have our request user at the top there, and that goes off and does something in a reactive style. And then we want to be able to return that as an actual user rather than a mono of user. So we call it, and we put block at the end, and we get back that value. We can do the same thing with a flux. And this is similar to an example that Ben used earlier. We again call request users, so we're going to get a flux of however many of them back. And we're going to call that method, we're going to collect it into a list, because we can't have a flux when we go into an imperative world. So we collect it into a list, we block again, and what we get is a list of user that we can pass on to the next process. So I've said that you can use block, and in many scenarios you will need to. But when we started out about 18 months ago, block was actually called .get. And one of the problems we had was that .get is a nice and friendly word. And you think, yes, I want to .get that value. I need this value so I can do stuff. And we'd have these reactive flows, and halfway through it would say .get. And it took months, probably, for us to really get the idea that, no, you've just broken it. If you have .get, then it's not reactive anymore. You've dropped down to an imperative mode. So partly because of that, Stefan changed the word to be .block, because that's aggressive and horrible and nasty. We don't like blocking. So that kind of helps you get this idea that, yes, you can use it, and if you're dealing with an imperative system, you will probably need to use it. But it's something you should think carefully about. As soon as you type .block, you think, no, I'm not sure I've done this right. Is this the right place for it? Can I push this out to the edge of my application and keep as much as possible reactive, and then only have it in that nasty, horrible place where I go imperative? What we found, in fact, we use it for testing, where we do sometimes need to block. And we have one method that contains, I think, all of our .blocks. So if you type .block anywhere else, you're doing it wrong. It must be because it's supposed to be in that method, that class over there, rather. Error handling. Errors are values, as we've said already. So you can't just say, oh, throw an exception, it's all gone horribly wrong. You might want to take an action on that error. You might want to...
Let me interrupt. There's a question in the back?
Yeah, I was just curious if there's actually, you get any advantage at all from using a reactor style if you end up using .block. If you're in imperative land, you go to reactive land, and you're still blocking your reactive part to actually execute, are you getting any advantage, or are you just having sort of like risk of advantage?
Yeah, so the question is whether if you have chosen to use block, you might go back a slide. If you've chosen to use block, has there been any advantage to going reactive in the first place? And I'd say the most likely case most people are going to use this is because they are in an imperative world, but they need to use an API like the Java client that is reactive instead. And surprisingly, the answer is probably yes, they have still gained an advantage, primarily because it's all non-blocking up until that particular point, or it blocks that outside thread. And so some of the things that we might do, right? So the fact that we spray out 15 requests simultaneously and let them all go in parallel with one another rather than doing this one, coming back, doing this one, coming back, doing this one, coming back. You've blocked this one thread, and no matter what, it's going to sort of take as long as it takes. But it has allowed us to go off and do a bunch of other sort of non-blocking things in parallel with one another in the meantime. But as a sort of a general thing, probably you're not getting huge advantage, especially if you don't know for sure that the API you're calling takes advantage of something like that, the ability to parallelize a bunch of behaviors. It's sort of hit or miss whether or not you're getting any advantage or not. Yeah. Oh, wow, okay. Yeah, so that's the question is, if I've got a blocking API but I'm in reactive world, how is there anything I can do to sort of make a blocking API reactive? And the answer is no. You can make a reactive API blocking, but you can't make a blocking API reactive, if that makes sense, kind of thing, because you're effectively what we would recommend doing there is sort of throwing it off onto another thread, not whatever sort of Nettie's incoming thread or something like that is, because it's gonna block. There's nothing you can do about it. And one of the weights of that caused us to make the Java client reactive in the first place was the idea that for the people who absolutely need a reactive API because they need this huge efficiency, they're making thousands and thousands of calls against the cloud controller each second kind of thing. Reactive and non-blocking is the only way they could deliver it. And we had no way to say, okay, I'm going to write this giant blocking API, but somehow I'm going to make this really efficient reactive for you. I can't go that way. Versus I can make a reactive one now, and if you're in a world that's not reactive, you can write 1 or 2 lines and get back to your imperative world much, well, at all, not even easier. It's the only way you can go. So there is a bit of that weighting it. We all have to deal with blocking APIs, even inside of reactive code. JDBC is the biggest one, JPA, stuff like that. And we generally recommend either isolating that kind of stuff off into another microservice if you're sort of a microservice kind of person. But if you're not, you've seen us use scheduler single, and basically, or scheduled on to scheduler single. And what that says is, when you get to this point in the execution, go throw this on another thread pool. And there's like an elastic one, and maybe there's a compute one. I can't remember what they all are. But we would generally say, okay, you should throw this onto another thread pool and release Netty to go off and do what it was doing before, so it can handle more network requests. And when that's done, Reactor will guarantee that it comes back onto a thread that is useful and gets returned eventually. You basically just fire it off to something that's not going to hold up the rest of the execution of the system.
So when you do that call to block, can you give it something to help protect your own thread pool? If you are down, you're deep in the nuts and bolts.
Yeah.
You've got a nice tuned reactive system off to the side.
Yeah.
Now you know you have to commit this in deep in the method. So you at least not host the current thread pool.
Yeah, you can push them off onto another thread, the same kind of scheduled on to put them somewhere else, but fundamentally, like in the middle, you've broken it. You've protected the, because there are, not all threads in this sort of scenario are created equal. The very small number of Netty threads traditionally is the one you absolutely have to protect because they handle every single incoming network request or every single outgoing network request in the case of clients going out. And blocking those means you block everything else, right? And so you can get something off onto another thread if you got to go do this, but you've thrown away most of the value that you have there. And so it's a good idea to sort of start protecting it. And this is very much a chicken and the egg problem today. There aren't many reactive APIs. We start seeing like data access APIs for, I think we've got Mongo and Redis today, RabbitMQ and messaging. I'm pretty sure Postgres has a reactive API that's not JDBC, but you can use to access it in a way. Oracle has stated that there's going to be an asynchronous JDBC or a non-blocking JDBC coming sometime. They've been saying it for a couple years, so who knows when we'll see it. And once we see that, who knows how long it is till we see non-blocking JPA as well. So like you do today have to protect around these things in a lot of places, but rather than ever using block, you should just say, okay, here's a blocking API over here. Let me throw that onto one of these other thread pools and then consume it as if it was non-blocking later on. Where you sort of, not all of, especially as you start taking a look at, sort of the slides we've seen from the Spring team, not everything in your code base has to go reactive simultaneously. You can have a controller that is exactly the add-MVC controller you've always known, switch to web Flux under without changing any code, and then just write a single controller method that's reactive, right? So not all your code has to go reactive simultaneously, but all of the code in a request chain has to be reactive in one go. That's the key there.
But did you just say the caller list users then needs to know to kick that whole call off to another thread pool as opposed to doing that somewhere deeper inside list users? Just trying to...
Yeah, the answer is it's up to you, and you can sort of decide whether or not it's useful for this person to be the person that's going to go off and schedule it. Generally, we would say, okay, if you need to, you've written some sort of repository that needs to go make a JDBC call, it should be the one responsible for saying, go kick this, because it knows that the call that it's about to make is a big problem. And so it's responsible for saying, I know this is going to block any incoming thread. So don't do this. And Reactor is really, really smart about this. Like if you're already on the other thread pool and you tell it to switch to that particular thread pool, it says, no, we're fine. We're not going to incur the price of the context switch to get there. And so it's not impossible, but it's unlikely you're going to put so many thread switches in there that you like seriously hamper performance in some way. Yeah. One up here. Is there a way to see how deep the request queue is? Yes, and you should go see a Reactor talk about that. Not really in the scope of this. Yes, there is instrumentation. They're working on UIs and stuff like that, so you can take a look at a flow as it's executing. And I've seen some prototype stuff that things get read and grow and shrink, and you can sort of see in real time all sorts of these metrics going by for a given request flow as it goes on. But the Reactor team is much better to answer that than I am. Yeah. One last one and we'll kick off again. You absolutely could have used block in a previous example instead of the CountDownLatch. Don't do it. Use StepVerifier, right? StepVerifier is a much, much better choice. We had some arguments over how much of those first couple of testing slides we were going to show because they show a lot of really bad stuff. It is exactly as horrible as you think it is. All the all the CountDownLatch that we use, not a great thing to do. You should absolutely use StepVerifier in testing. It's the only thing you should really be doing. In the main method, maybe, sort of that example block is the correct answer. But from my perspective, like, get in the habit, right? If you are thinking about asynchronicity and non-blocking I/O, just stick with it. Yeah, it sucks to write a CountDownLatch and the subscribe with the 3 parts, but like, I've got a macro in IntelliJ that writes it all for me, right? It sucks, but it keeps me in this mindset of never, ever, 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 ever write block. You've written block, you've done it wrong, right? Like, you don't want to be in a habit where anytime I'm writing code, I can't write blocks. Anytime I'm writing tests, I can write blocks, and now you just sort of get sloppy between the two of them, right? Okay, so let's kick back off here.
Okay. Okay, so when we're doing our error handling, we've got the same sort of thing that we were seeing before. We're going to start with a flux. This one's a little bit different because one element in that flux is a string, a mono just of alpha. But the other one is an illegal state exception. As we've said several times, exceptions are the same as any other value. They can be passed down, they can have meaning, they can just be passed on to the person who's following. So in this case, we're still using our CountDownLatch. We're going to subscribe to it. We're saying I want to print out whatever I get, which will work for alpha just fine. But the second step is we're going to, if there's an exception, we know there will be, then we want to print the stack trace. And we still want this thing to complete, so we're going to free our CountDownLatch. And the final line says latch countdown. So whatever happens, if we get an on-complete, we want to make sure that we release the latch. Composable method references. So we're potentially chaining together lots of things, which means we're at risk of callback hell, but we don't have to be if we're careful about things. If, for example, we extract behavior into private methods, we want to keep things nice and succinct. Ben talked about his Ruby experience, which has really played into the way that we code. So by having well-named methods, it starts to feel more like you're reading instructions, and then deep down underneath, there is actual Reactor going on. So if we use this as an example of that, I'm getting an application summary. Now, even if you don't know anything about Cloud Foundry, I think you can kind of follow the logic of this statement here. I'm going to start with a Cloud Foundry client and a space ID, some things that I need. I'm going to pass that information in to get a request space summary. Don't know what that is, doesn't matter. I'm then going to use the information that it provides to extract the applications. I'm going to take application information from that request space summary. And finally, I'm going to map, so I'm going to convert this into an application summary. So there's all sorts of cleverness going on underneath that, all sorts of Reactor. But at the high level, I can say exactly what it does. Nice and straightforward. One of the things you may have noticed is that we're using a style called point free. If you're strictly imperative, this might look a little odd to you at the moment. So the idea is that rather than creating a variable with a particular builder that we're using and then using that variable, we just put it all effectively in line. There's a link there you can go to if you like Haskell that will tell you all the reasons why it's a good idea. If you don't like Haskell, don't go. The idea is that we can, rather than worrying about marshalling all these variables, we can just write the code that we want and say, I need this to do this thing. So we're thinking at a higher level rather than worrying about variables. We had huge debates when we started off. Ben insisted that this point-free thing was a fad and horrible and we shouldn't do it, which is why we made him rewrite all the stuff that he made us do the wrong way. So we've reached the point where you may react against it. You may think that this example, for example, just looks really crowded and dense and I can't quite see what's going on. But eventually you find it actually becomes second nature and it's much more informative and you can understand what's going on more easily. So if you look at that first one, for example, the list applications request, I could have created a separate builder variable and then just inserted that in that line. But when I make my second request, you can see it uses an application ID that comes out of the flow. So I can't really build that in advance. I can do it, but it starts to get clumsy. So it's much easier if I just do it in this point-free style. And in actual fact, I wouldn't even do it like this because I would have a couple of method calls, one that did the list applications request and one that did the delete application request.
I'll be the first to say today that there is no way that that example is improved by the addition of equal signs anywhere in it, right? You end up with a lot more lines, a lot more noise, and it's a lot more difficult to understand. I mean, like, this is clearly dense anyway, and adding bunches of white space and assignment and stuff like that so that you can keep track of variables is confusing in the end. I am definitely a convert today.
Okay, so I'll hand back over to Ben for the summary.
Great. So to close this thing out, amazingly, we're right on time. So we've talked a bit today about what it means to design a reactive API. And obviously, the very first decision when it comes to designing a reactive API is, should I design a reactive API? And the answer, especially in these early days, is often no. Right? The more I talk to customers who are starting to use this kind of thing, I realize that what's going to happen is, in the beginning, people are going to look at it and they're going to say, okay, there are a couple things. We're doing a lot of networking, or we've got this thing where we're running out, we've got horizontal scalability because we need all these connections, and yet we aren't using the CPUs. Great. We're just going to work on that. But and everything else is going to stay exactly as it is. We're going to start new projects that we don't think are going to have this particular project, and they're all going to stay imperative. But eventually, you're going to have a team that is conversant enough in reactive programming that they will be more productive staying in reactive programming, even in places where it doesn't actually make a huge difference. And so they'll start implementing things that way over there. And what you're going to end up with, like teams, I suspect, that are really, really good at this. They know all the styles of debugging, and they've sort of forgotten a lot of their imperative programming style. And they'll be really, really good. And some companies, that team will infect the entire company, and everybody will have gone to reactive whether they wanted it or not, because there's a lot of tooling around it, maybe. And then you're going to get other companies that never go to reactive and just like, horizontal scaling. And I suspect somewhere in the middle, there's going to be people who selectively choose to do reactive projects where reactive projects make a lot of sense. You're always returning mono and flux, can't return void anymore, and you want to have reusable methods, right? Sort of adopt some of these other languages, patterns, things like Ruby, Node, Go is exactly the same way. Really, really small, compact methods, really descriptive names, so that when you read high-level flows, you start seeing something that you understand without having to see all of the mechanics of what's going on. When you go off to implement things, remember that for the most part, you're going to end up with Reactor, or whatever your reactive framework is, sort of dealing with whether or not things should execute sequentially or parallel for you. So things like, if you execute a flat map, in all likelihood, that's going to happen in parallel. You won't know it, but it does actually happen. And so depend on the framework to do most of the thread management for you, but remember that you do have the ability to make decisions about thread management in places where the framework can't make a great choice. Conditional logic obviously can be implemented using the operators that we've seen, but don't be afraid of using imperative conditional logic. It's absolutely the right choice in a whole lot of places, simply because it's so much easier to read. And then finally, we talked quite a lot in here about testing. StepVerifier. It's the only answer you need to know. There are a bunch of different ways, but you should absolutely test. You should absolutely depend on all these things being asynchronous and non-blocking, and JUnit's going to hose you because of it. Use StepVerifier, takes care of all of those problems for you, has a really robust API for doing assertions or writing your own custom assertions inside of it. When it comes to use, I like CountDownLatches. You don't have to like CountDownLatches. You can use blocking and stuff like that. But again, it comes back to that opinion I have that you should just get in the rhythm, right? You should get in the rhythm that nothing ever blocks. Nothing ever blocks. You never make a mistake if you never think about blocking in the first place. You have to handle errors on your own. Make sure you're using composable methods, as we've seen. Method references in Java 8, really, really useful for this. Write really good method names. Because remember, as we all know from Spring's API, The first 64 characters of a method name are used to discriminate, but you can make a method name as long as you want. Like we've got a 217 character long method name down in the AOP stuff. So make nice descriptive names for things. And then finally, the point free style. I made a mistake, don't make my mistakes, right? Point free style really, really does work. You're never gonna, once you start, if we went back, we should probably add another slide in there that shows what that looks like with all the equal signs, and no one's gonna think it's any better. So with that, if you all are interested in sort of a much, much deeper dive, the Cloud Foundry Java Client project has a couple 100,000 lines of production code, has a couple thousand tests using StepVerifier and things like that. It is a great place to see all of the stuff that we have talked about here actually implemented in real life. We're developing on it every day. Things are changing, things are improving as we find more styles and stuff like that. But this is the real deal, right? This is a real live API in production use in a lot of places, whether it's the banking industry over in Europe or Pivotal itself running it internally. There's airlines here running it as well. And so it's a great example for us to have. Paul and I thank you all for coming. We'll be happy to take any Q&A below. Thank you.